This is a credit card. Harmless enough. Its magnetic strip holds your financial data, encoded in particles aligned by a weak magnetic field. Now imagine something 1 trillion times more powerful. Not in another galaxy, not in some unreachable corner of the cosmos, but lurking right here, in our own Milky Way. Meet the Magnetar. If a magnetar passed within 500,000 miles of Earth, farther than the Moon, its magnetic field would be strong enough to erase every credit card, hard drive, and magnetic device on the planet. But that would be the least of our problems, because at that distance, the tidal forces from its gravity would tear our world apart. And if we somehow survived, the magnetic field itself is so powerful that it rearranges the very atoms in your body. Your molecules would literally no longer work. This is an object where the laws of physics don't just bend, they break. In the next minutes, we're going to witness the most violent event ever detected from deep space. We'll meet the maverick scientists who refused to believe the instruments were broken. We'll discover how a dead star generates a magnetic field quadrillion times stronger than a hospital MRI. And we'll journey to 2025, where astronomers just solved one of magnetar science's greatest mysteries. This is the story of cosmic monsters hiding in the shadows of our galaxy, waiting to burst. March 5th, 1979, 10:51 Eastern Standard Time. Two Soviet spacecraft, Venera 11 and 12, were coasting through space on their way back from Venus, their radiation detectors humming with normal background counts. About 100 particles per second, the usual cosmic hiss. And then, in less than 1 millisecond, the detectors jumped from 100 counts per second to over 200,000. Within seconds, 9 satellites across the solar system lit up. Earth's ionosphere, normally ionized by sunlight during the day and neutral at night, suddenly blazed with energy. At 11 p.m. local time, it looked like noon. Because the instruments were scattered across different distances, some near Venus, some orbiting Earth, scientists could triangulate the source by comparing when each satellite detected the pulse. Light travels at a fixed speed. If you know the distances and the arrival times, you can work backward to find the origin. The answer shocked them. The burst came from the Large Magellanic Cloud, a small galaxy orbiting ours, 160,000 light-years away. Think about what that means. Something 160,000 light-years away. So distant that its light takes longer to reach us than modern humans have existed on Earth. Released enough energy in 1/5 of a second to saturate instruments across our entire solar system. The calculations showed this object had emitted, in that fraction of a second, twice as much energy as the Sun had produced in the previous 5,000 years, since the pyramids were built. Scientists had no idea what they'd just witnessed. It looked like a gamma-ray burst, the catastrophic death scream of a massive star collapsing into a black hole. Except, gamma-ray bursts don't repeat. They're one-time events. This source kept flashing. Softer bursts, shorter, again and again from the same spot in the sky. They called it a soft gamma repeater, SGR for short, and for over a decade, no one could explain it. The answer, when it finally came, would reveal the existence of the most extreme objects in the known universe. To understand what creates a magnetar, we need to start with something more familiar. A star. Not our sun, something much larger, 20, 30, maybe 40 times more massive. For millions of years, this stellar giant burns through its nuclear fuel. hydrogen fusing to helium, helium to carbon, carbon to oxygen. Each fusion reaction produces outward pressure that fights against gravity's inward crush. But eventually, the star runs out of fuel. The core, now made of iron, can fuse no further. Iron fusion consumes energy instead of releasing it. The pressure vanishes. And in less than a second, gravity wins. The core collapses so fast that electrons and protons are crushed together, forming neutrons. The entire mass of a star, crushed into a sphere the size of a city, 10 to 20 kilometers across. If you took Manhattan Island and compressed it until it was 1 centimeter thick, you'd be approaching the density of a neutron star. A teaspoon of this material weighs 100 million tons. The star's outer layers, everything that isn't the core, explode outward in a supernova. We see it from Earth as a brilliant new star, fading over weeks. But at the center, invisible to the naked eye, something extraordinary remains. A neutron star is unlike anything else in the cosmos. Its surface gravity is 2 billion times stronger than Earth's. If you dropped an object from 1 meter above the surface, it would hit the ground at nearly a third the speed of light. And despite being made of the densest matter we know of, it has a solid crust, half a mile thick, made of atomic nuclei squeezed into a crystalline lattice, 10 billion times stronger than steel. Below that, a sea of superfluid neutrons and superconducting protons, matter behaving in ways we can only glimpse in our most advanced physics labs. Every neutron star has a magnetic field. The star's original field, already strong, gets compressed as the star collapses. Having a star's radius quadruples the magnetic field strength. For most neutron stars, that's the end of the story. You get a pulsar, a lighthouse in space, beaming radio waves as it spins, sometimes hundreds of times per second. But about 1 in 10 neutron stars takes a different path. In 2025, an international team led by scientists at Newcastle University, the University of Leeds, and institutions in France finally cracked one of magnetar science's biggest mysteries. How do these extreme magnetic fields form? Here's what they discovered. When the supernova explodes, not all the outer material escapes. Some of it, perhaps 10%, falls back onto the newborn neutron star. This fallback material causes the neutron star to spin faster. And inside the proto-neutron star, still hot, still turbulent in those first few seconds after birth, something remarkable happens. A dynamo kicks in. Not the kind you'd see in a power plant. This is a magnetohydrodynamic dynamo, the Taylor-Spruitt mechanism, where the star's rotation, combined with its intense heat and conducting fluids, generates loops of magnetic field. These loops twist, merge, amplify. The magnetic field, normally around 100 million Tesla, already unimaginably strong, explodes to over 100 billion Tesla. That's a quadrillion times stronger than Earth's magnetic field. 1 billion times stronger than the most powerful magnet ever built by humans. At these field strengths, atoms cannot exist. The magnetic field rips them apart. Matter itself takes on bizarre quantum forms we can barely calculate. The result is a magnetar. Back in 1979, astronomers knew they'd witnessed something incredible. But what? The source, now designated SGR 0525-66, kept repeating. Bursts of gamma rays and X-rays, lasting fractions of a second, flaring unpredictably. For 13 years, scientists debated. Was it some exotic kind of binary system? Two objects orbiting, occasionally colliding? Was it matter falling onto a black hole? Then, in 1992, two physicists at the University of Texas, Robert Duncan and Christopher Thompson, published a radical idea. What if the bursts came from a neutron star with a magnetic field so strong that it literally broke the star's crust? They called them magnetars, and they proposed something extraordinary. The magnetic field is so powerful that it stresses the star's crust. The crust bends, warps, cracks. When it finally snaps, a starquake releases energy equivalent to a magnitude 32 earthquake on the Richter scale. For comparison, the largest earthquake ever recorded on Earth was magnitude 9.5. But would the scientific community accept this? Enter Krissa Kuveliotu, a NASA astrophysicist who'd been studying these mysterious soft gamma repeaters for years. She decided to test Duncan and Thompson's theory directly. In 1998, she used NASA's Rossi X-ray Timing Explorer to stare at one of these objects, SGR 1806-20, and wait for it to burst. And there it was. The object was pulsing, spinning with a period of 7.47 seconds, slow for a neutron star. And as it spun down, losing energy, she could calculate how strong its magnetic field must be. 800 trillion times Earth's magnetic field. The magnetar theory was confirmed. These weren't just neutron stars, they were magnetic monsters. If March 5th, 1979 was the discovery, December 27th, 2004 was the wake-up call. It was a quiet morning. Satellites monitored weather, GPS systems guided travelers, communication networks hummed along. At 21:30 Universal Time, Earth's ionosphere exploded with energy. From the night side of the planet, dark, quiet, suddenly particles ionized as if the sun were directly overhead. The gamma-ray burst was so intense that NASA's SWIFT satellite had to shut down to prevent damage. RXTE, wind, BEPO-SAX. Satellites designed to detect cosmic radiation were completely saturated. Fishermen in the Arctic saw a sudden aurora at the equator. Radio communications briefly failed. For a tenth of a second, Earth's ionosphere changed from night to day. The source? SGR 1806-20. The same magnetar Kuveliotu had studied 6 years earlier. This magnetar sits on the opposite side of our galaxy, 50,000 light-years away, hidden behind the galactic core, invisible in optical light. In 1/10 of a second, it released more energy than the Sun emits in 150,000 years. Astronomers immediately did the math. If that burst had come from a magnetar just 10 light-years away, still far by everyday standards, it would have stripped away Earth's ozone layer and caused a mass extinction. The nearest magnetar we know of is 9,000 light-years away in the constellation Carina, still comfortably distant. But here's the thing. Magnetars are small, dark, and quiet most of the time. We've only confirmed about 30 of them. Statistical estimates suggest there could be 30 million inactive magnetars in our galaxy alone, lurking unseen. Most of them are hidden in dust lanes and behind gas clouds, silent, waiting for something to trigger the next great flare. So what exactly happens during these giant flares? Why do magnetars suddenly explode with energy? It all comes down to a battle between two forces. The magnetar's crust, That crystalline lattice of atomic nuclei we talked about earlier is incredibly strong. But it's also frozen in place, and threaded through it are the magnetic field lines. The problem? The interior of the magnetar, that superfluid sea of neutrons and superconducting protons, can rotate at a different speed than the crust. As it does, the magnetic field lines twist. Imagine twisting a rubber band. 1 turn, 2 turns, 10 turns. Eventually, something has to give. The crust fractures. A starquake rips across the surface at speeds approaching the speed of light. When the crust breaks, the magnetic field lines snap and reconnect. This releases an enormous amount of energy, stored in the magnetic field itself as high-energy photons, gamma rays, X-rays. And there's something else. The magnetar isn't sitting in a vacuum. It's surrounded by a magnetosphere, a sea of charged particles trapped by the magnetic field. According to observations published in 2025, these particles are accelerated to nearly the speed of light by the shifting magnetic fields. When they slam into each other, or into the star's surface, they create matter-antimatter pairs, electrons and positrons. And when matter meets antimatter, they annihilate, producing the gamma rays we detect. It's E equals mc squared running in both directions. Energy becoming matter, matter becoming energy, all within milliseconds. Recent studies using NASA's IXPE satellite, the Imaging X-ray Polarimetry Explorer, have even measured the polarization of these emissions. And what they found is stunning. The magnetic field is so strong that it can turn the magnetar's atmosphere into a solid. This phenomenon, called magnetic condensation, means that above certain field strengths, the vacuum itself crystallizes. Empty space becomes structured. And as scientists dug deeper into magnetar behavior, they discovered something entirely unexpected, a connection to one of astronomy's greatest mysteries. While magnetar science was advancing, a completely separate mystery was brewing. In 2007, astronomer Duncan Lorimer was sifting through old data from the Parkes radio telescope in Australia when he found something bizarre. A burst of radio waves, incredibly bright, lasting just 5 milliseconds and coming from billions of light years away. Over the next decade, more bursts appeared. Fast radio bursts, FRBs, intense, brief flashes of radio energy from distant galaxies. Most appeared once and were never seen again. A few repeated unpredictably. What could generate that much energy in milliseconds? Colliding neutron stars? Black holes? Alien technology? Then, on April 28, 2020, the Canadian Hydrogen Intensity Mapping Experiment, CHIME, detected an FRB. But this one was different. It came from inside our own galaxy, just 30,000 light-years away in the constellation Vulpecula. The source? A known magnetar, SGR 1935 plus 2154. For the first time, astronomers had caught a magnetar producing a fast radio burst. The two phenomena, magnetars and FRBs, were connected. That single detection opened the floodgates. Radio telescopes around the world pivoted to study magnetars, hoping to catch them in the act of producing FRBs. And in January 2025, a team at MIT made a breakthrough. They pinpointed the exact origin point of an FRB, designated FRB 202-21022A, using a technique called scintillation. As light passes through Earth's atmosphere, it bends slightly, creating the twinkling effect. The same thing happens when radio waves pass through the gas in galaxies. Crucially, the smaller and brighter the source, the more it twinkles. By measuring the scintillation of FRB 202-21022A, the team could calculate the size of the emission region. The answer? The burst originated no more than 10,000 kilometers from the Magnetars' surface. That's less than the distance from New York to Singapore. In cosmic terms, it's touching the surface. This proved, for the first time, that FRBs can originate directly from a magnetar's magnetosphere, the region of super-strong magnetic fields immediately surrounding the star. Throughout 2025, the picture became clearer. FRB 202-40114A, detected in January, produced over 11,000 bursts in just 214 days, the most prolific FRB ever observed. FRB 202-40209A stunned astronomers by coming from the outskirts of an ancient, dead galaxy, not a region of active star formation, but possibly a globular cluster where magnetars form through neutron-star mergers. What these discoveries revealed is that magnetars are far more diverse than we'd imagined. Some are young, born in recent supernovae. Others are ancient, formed through the merger of two neutron stars billions of years ago. Some burst constantly. Others stay silent for decades, then suddenly explode with energy. They're not a single phenomenon. They're a whole ecosystem of extreme physics, hiding in plain sight across the universe. As of late 2025, we've confirmed 30 magnetars in our galaxy, and likely detected dozens more through their fast radio bursts across the cosmos. Here's what we know. First, magnetic fields form through a dynamo process in the first few seconds after a neutron star's birth, amplified by fallback material from the supernova. This 2025 discovery finally explains how magnetars get their extreme fields. Second, the giant flares, like the 2004 event, happen when the magnetar's crust fractures under magnetic stress, releasing energy through magnetic reconnection and matter-antimatter pair creation. Third, magnetars produce fast radio bursts from their magnetospheres, where particles accelerated by shifting magnetic fields emit intense radio waves. This connection was only confirmed in 2020 and refined through 2025. Fourth, not all magnetars are the same. Some have low magnetic fields, still a billion times Earth's, formed through different mechanisms. Some are young, some ancient. Some burst frequently, others rarely. But for all we've learned, mysteries remain. Why do only some magnetars produce FRBs? What determines the burst rate? How do magnetic fields evolve over millions of years? Could there be even more extreme magnetic objects we haven't detected yet? Every answer opens new questions, and that's exactly as it should be. Let's step back, way back. Because magnetars aren't just exotic curiosities, they're laboratories. On Earth, even in our most advanced facilities, we can't create magnetic fields stronger than about 100 Tesla. The strongest continuous magnetic field ever produced by humans at the National High Magnetic Field Laboratory is 45 Tesla. A magnetar's field is 10 billion times stronger. At those field strengths, physics behaves in ways we can't replicate. Quantum chromodynamics, the force that holds quarks together, is directly affected. The vacuum undergoes phase transitions. Space itself crystallizes. By observing magnetars, we're testing theories that would otherwise remain purely mathematical. We're seeing nature push the laws of physics to its absolute limits. Remember the Schwinger effect from our Kugelblitz episode? The quantum process where intense electromagnetic fields create matter-antimatter pairs. We see that happening in real time on magnetars. And there's more. In 2025, physicists used gravitational wave detectors to search for signs that magnetar starquakes might generate ripples in space-time. So far, no detection, but the search continues. Think about what that means. We're sitting on a tiny, fragile planet, orbiting an unremarkable star in the suburbs of an ordinary galaxy. And yet, we've built instruments sensitive enough to detect the faint radio whisper of a neutron star 30,000 light-years away. We've measured magnetic fields 1 billion trillion times stronger than anything on Earth. We've triangulated the source of gamma-ray bursts from neighboring galaxies. We did this through mathematics, cooperation, and sheer determination to understand. Here's something worth pondering. Magnetars are the most violent, destructive objects that aren't black holes. Their giant flares can sterilize planets from thousands of light-years away. Their magnetic fields can tear apart the atoms in your body. And yet, we're safe. The nearest known magnetar is 9,000 light-years away. Too far to harm us, even during its most violent outbursts. Now, could there be closer ones we haven't detected? Certainly. Magnetars that have been quiet for decades or centuries wouldn't show up in our surveys. They're just cold neutron stars with no distinguishing features until they suddenly burst. Statistical models suggest there could be millions of dormant magnetars in our galaxy. Most will never threaten us. Space is vast, and we're unlikely to be in the line of fire. But isn't that remarkable? That we exist in a universe violent enough to create these monsters, yet structured enough that we're here, safe, able to observe them from afar. The same supernovae that create magnetars also forge the heavy elements that make up planets. And us. The iron in your blood, the calcium in your bones, the oxygen you breathe. All of it came from stars that exploded. Magnetars are part of the same cosmic cycle that created the conditions for life. They're not threats to be feared. They're siblings in the story of matter. The story of magnetars isn't finished. It's just beginning. The square-kilometer array, when completed, will be 50 times more sensitive to radio bursts than current telescopes. We'll detect thousands of FRBs, pin down their origins with incredible precision. The Einstein telescope and Cosmic Explorer, next-generation gravitational wave detectors, might finally catch the space-time ripples from starquakes. And new X-ray observatories, launching in the next decade, will measure magnetar magnetic fields and plasma behavior with unprecedented detail. But it's not just about bigger telescopes. Physicists are developing new theoretical frameworks to understand how matter behaves at these extreme densities and field strengths. We're simulating neutron star interiors on supercomputers, testing whether quarks might exist freely inside the core. We're calculating how magnetic fields evolve over millions of years. And here's what I love. Anyone, anywhere can participate. Amateur astronomers have contributed to magnetar science by monitoring optical flares. Citizen science projects analyze radio burst data. Students write code to model magnetic field evolution. The questions are open. The data is published. The universe doesn't discriminate about who gets to understand it. So the next time you look up at the night sky, remember, scattered among those points of light are objects so extreme they defy imagination. Stars where the magnetic field is strong enough to dissolve you at a distance of 1,000 kilometers. Where a single starquake releases more energy than the sun produces in 1,000 centuries. They're not just destructive. They're magnificent. They're nature's way of showing us what's possible when physics is pushed to its limits. And we, tiny, fragile, brief, have figured this out through patience, mathematics, and wonder. The universe is knowable, even its most violent corners, and we're the ones brave enough to look. This is Cosmic Canvas, where curiosity becomes a magnetic force of its own. Until next time, remember, when space cracks and stars quake, we're still brave enough to listen.